All right, hello everyone. In this video, we continue our discussion on different kinds of forces in physical systems. In the last one, the same series, we saw how we could understand projectile motion and classify it under category of motion under gravity, right? So for motion under gravity, the resultant force is F equals to mg, right? So we are sort of focusing on the resultant forces that arise under conditions where different forces govern the motion or govern the energy changes that are taking place. So when an object is thrown up or it's falling downwards, it's the gravitational force that causes change in GPE or KE, right? So this is for motion under gravity. Similarly, for an object that is, say, for instance, floating in water or submerged in water, right? Let's say, for instance, an object, okay? Mm, its weight is acting downwards, and there is an upthrust acting upwards. Just fix this again. So U and W. So in this case, there is a buoyant force, as we call it, or upthrust acting on the system. So this depends on the volume slash mass of water or any liquid in which it is floating in. This plane. So this force is actually given as V rho G, where V equals to this volume that we are talking about. Rho represents density of the fluid. And G, of course, acceleration due to gravity. All right. So in a system where you see an object floating in water or submerged in water or floating in oil, submerged in oil or whatever of that sort, okay, in that case, the upthrust force, which is acting in a direction opposite that of the weight, is given by this. So whether it will float or it will sink or it'll be half submerged or whatever, okay, that is governed by this force. Let me just rename it. It's easier that way. Let's call this U. So the resultant force is always the difference between W and U. This sign signifies difference between two physical quantities, which means either U can be greater than W or W can be greater than U, or they can be equal, in which case the resultant force will be zero in the system. They'll be in equilibrium. Okay, so that's another example. So basically we are just looking at various kinds of physical forces in a given system that can play a role in determining resultant forces. All right. Another commonly encountered example is, say, a spring. Okay, so this is a spring. and this is of the same spring when it's loaded. So this is, say, L or L naught, the initial length. This is the final length. So we have x equals to L minus L naught, which is called the extension. Now, it is common knowledge that the extension is taking place because of the weight that is hung at the end of the spring, right? So if we look at it this way, then the force that is pulling the spring, extending it, that is on account of this weight. So mg can be thought of as a resultant force, right? And that is actually equal to kx. Now, this same mg won't act similarly on all kinds of springs, because different springs have different extensibilities, different springs have different kinds of stiffness, as we like to call it. So that factor is taken care of by K, the stiffness that helps pinpoint on what kind of spring we are using. Stiffness constant of force constant into X, which is the extension, which makes sense, right? So something that's more stiff will extend less under that same weight. Whereas if there is a less stiff spring, it's more likely to extend and change its shape. In that case, the K will be smaller, so X can be larger. All right. So this is another example of how resultant forces act on given systems, right? Now, one thing to note is that Kx is on account of this, but Kx is actually acting upwards. It is trying to pull the spring back to its position. So once this mg is removed, it hurries back to its original position to reach L naught as fast as it possibly can. And that is on account of Kx. So we will see in later chapters that this Kx is actually the reason why, if we remove the pulling force, it tends to oscillate. Okay, so this Kx is not as simple as it seems, but from a purely mechanical standpoint, Kx just represents the resultant force acting on the spring on account of the load acting on it. Now, one thing that I have not mentioned for any of these three is that they are all idealized scenarios. I have not considered a realistic situation. And why is that? It's because if there is motion under gravity, there is another force that is also acting in this case, something that is extremely important, and that is air resistance. We briefly discuss it in our energy video and how that affects energy changes taking place. But here, air resistance or drag acts on a given system as it moves through air, which is a fluid. All right. So it's the same thing as when you're trying to stir water vis-a-vis when you're trying to stir honey. Stirring honey is a little more difficult, right? Everyone knows that. The reason being that the motion in that particular fluid is resisted more by honey, right? You use the same spoon, right? But the same spoon is being affected differently in honey compared to that in, say, water or oil, right? Because of this property called drag or viscosity, to be more scientific. So the more viscous the fluid, the more it resists, right? Motion that is taking place through it. So we did not consider air resistance over here, and we only considered gravity as the overriding force. So that's an assumption that we made. Similarly, over here, we consider that the liquid is incompressible, which means there is no change in the internal properties of the liquid. There was no change in volume of the liquid on account of this object being present in it. Primarily because, say, this small block was submerged in a huge tank or a huge pool. So the change in volume suffered by that particular entire the pool of water is negligible compared to the volume of this object in an internal sense. Of course, it displaces water as it's placed in it. And depending on how much it displaces, this upthrust will act, and that will determine whether it will float or sink or, you know, display some other kind of accelerated motion. All right. So here we consider an incompressible fluid. That brings us to our third example. Here, this force is called the elastic force sometimes, primarily because the spring is elastic and it tries to retain its original configuration as soon as the deforming force is removed. In this case, the deforming force is mg, right? It's elastic force. So in this case, the assumption is the spring is massless. It's very, very light. Okay, and the mass of the spring is far less than the mass of this object that is deforming it. Otherwise, the problem is, if the mass of the spring is not negligible, that means it is already extended under its own weight, because the weight of the spring will also act downwards like this. But we consider this to be negligible, and only this to be sufficient or considerable enough to cause a change in the shape. All right. So consideration of any of these forces would result in a more realistic modeling of the physical phenomena that is taking place. Now, though we don't really talk about how these any of these really make a difference, we do talk about air resistance a bit, and how air resistance is affected by a couple of factors. So we will look at that now. These are important for you to know so that you understand what are the assumptions, what are the constraints that you are working under, so that your mind does not divert towards these factors. Because you might think, why is the weight of the spring not being taken into account? Because of this assumption. This is much, much less compared to this. So we can, for all practical purposes, as we like to say it, right, makes it sound very official. For all practical purposes, this is the dominant force here that is governing the elastic nature, or affecting the elastic nature, showcasing the elastic nature, right? And there's no change in the bulk properties of or the internal properties of the fluid, right? On account of this object being there, right? Again, consideration of this would be a more realistic scenario, but then it does not really affect our study because, like I mentioned, the volume of this object and the volume of the water, the total volume of water that we have considered, that is far too great for this to cause any significant change in the bulk properties of the fluid that is there in question. All right, so moving on. So if I look at air resistance, there are two things. You'll find it in your textbooks as well. But there are a few things that I wanted to talk about in terms of air resistance. The things to always consider. It is a force that is acting on account of motion of the object. So it is resistance to motion within a fluid. This is where it is distinct from another kind of resistive force that we discussed before, and that is friction. As I discussed in another video, depending on whether you've watched it or not. They're distinct from friction. All right? So an object that is at rest within a fluid, this does not act. For example, again, in our discussion before, we're looking at this buoyant force and everything. This object is at rest within the fluid, so I don't need to consider air resistance over here, or any other, or maybe water resistance over here. Viscous, because water is also viscous, so it also showcases the property of drag as soon as an object starts flowing through it. All right, so it's an account of motion, and it's a resistance to motion within a fluid, which distinguishes it from friction, which is resistance to motion of one surface over another, right? And it affects the system because of two factors. First is velocity of motion, and the second is surface area of object. Two very important factors. Again, the very fact that the air resistance force is dependent on velocity kind of dictates the fact that, okay, if there is no motion, then this does not really make a difference. Okay, so how fast the object is moving, air resistance takes that into account and tries to close it. It's like when you're moving through a crowd. If you try to run, you face a greater resistance compared to when you're trying to make your way slowly through a crowd. All right? The second one takes more time, maybe, or you think you perceive that it would take more time, but in reality, if you try and force your way through a crowd, it will actually take a greater interval of time than the former, because you will face greater resistance. So you'll have to overcome that resistance again and again. So maybe your velocity will reduce to zero. Whereas in the second case, your velocity was almost steady throughout, reducing a little bit when the crowd was a little bigger, and then you snake your way past it, and then maybe you could increase your speed again a little bit, and then again it reduced again. But the reduction was far less than when you were trying to run through it and faced a greater change in velocity on account of the resistance that you faced, and that thereby reducing the overall speed, the average speed that you have. All right, so that's how velocity affects surface area. Of course, you're I mean, like, there's no body shaming here. You're a lean guy or a lean girl. I mean, like, moving through the crowd, you're more likely to face less resistance. Just weave your way past through every obstacle that you get. But if your girth is not negligible, if you have been hulking up on all those protein shakes and such like, right, you are more likely to face more resistance. Now this, moving away from this example, imagine a supersonic jet with a blunt nose, right? Think about it. That's one reason why supersonic jets and fighter jets, or the stealth bombers that you see, or for that matter, any other system that needs to move at very high speeds through fluids, be it air, be it water, be it anything, any fluid, their tips, the tips of their noses, they are extremely pointy, they are sharp. The area of cross section is negligible, it's very, very small. That's the reason. Because if it were blunt, then it would face a far greater air resistance, not allowing them to reach those very high speeds that they are aiming for. So the surface area of the object is extremely important. It should the surface area that is exposed to the fluid directly along its direction of motion within the fluid, that is reduced. That should be reduced. All right. So all those supercar fans over there, your cars have a specific shape. You don't have a hatchback, right? You can't have hatchbacks as supercars, and that is the reason, because the aerodynamic of the hatchback is quite different, and it's not equipped to handle those very, very high speeds that a supercar is supposed to achieve. And in order for that to be true, the aerodynamic, the entire body of the car is shaped in a manner that actually tries to negate air resistance acting on it. So airflow along the car is shaped in such a way that it would affect the motion of the car in the least possible manner, because we know that this makes sense. If a supercar moves at a speed of say 200 kmph, the velocity is pretty high, so air resistance will be pretty high, right? If you try and put your hand out through the window of probably a Bugatti or a Koenigsegg or a Pagani, right? You'll feel that, right? The wind is pushing your hand backwards, and that effect is the effect of air resistance. That won't happen if you are probably traveling in a Toyota Prius, for example, right? You put your hand out, I mean, like, it won't reach that high velocities where the resistance will be high enough for you to have your hand pushed back. I mean, that's a very dangerous proposition. Please don't do that at home. These stunts are really always practiced by trained professionals, right? The disclaimers that they always give us. So that's how it is. And therefore, in fact, a very important and a very intuitive thing that we see, the max speed in a car is actually the maximum air resistance that it can take. How, you ask? Because when a car is moving, say in the forward direction, that's the driving force of the engine, and this is your air resistance R. So by a knowledge of forces, we know F minus R equals to ma. Now as velocity increases because of the driving force, right, this also increases. Right, till a time is reached when F is equal to R and velocity equals to constant, and that is your max speed. So if a car has a maximum speed limit that is say 160, then it can only handle the air resistance. The engine can only provide that much force. It can overcome that air resistance at 160. So that's how you get the idea of max speed in a moving vehicle. So air resistance and its considerations are extremely important for us, right? For example, the most hackneyed example that we have, a parachutist diving, right? When do you open the parachute? When this condition is met. So in case of a parachutist, it is mg equals to r. It is only then that you can open the parachute. Otherwise, if any of them are high enough, then you are in danger of losing a limb. Pretty graphic, but true. So when R equals to mg, you open the parachute because you're in equilibrium. As you open the parachute, area of cross section increases, and then what happens? Your velocity, in fact, reduces, because area of cross section increasing means air resistance increasing suddenly. So there's a jerk. So if the jerk is encountered by the human being when R is not equals to mg, So the person opens the parachute and R is not equals to mg. There is an added jerk, right, which kind of rips the parachute off of your body, and you're in grave danger, right? So you won't want that. Okay. So R equals to mg. As you open the parachute, surface area increases. This again increases, right? And so velocity reduces, right? Because the acceleration is because of the air resistance, which is upward, and you're falling downward. Now, as that happens, again, as this acts and reduces the velocity, then again it itself reduces, right? Because it cannot act at that higher value, the velocity reduces. So again, this takes up center stage. So the object keeps falling under gravity, even though the parachute is there, right? And then again, you reach a condition where the person keeps falling, his velocity increases again, but not to that high an extent because the parachute is open, and because this can also increase to a greater extent right now. And then again, this is reached a second time round, and that at that second time, the person is down on the ground and with a far less velocity than initially obtained when the parachute was open. So if the parachute was not open at this point, you would have fallen with this velocity, this constant velocity, and that would have been fatal for the person because this velocity is extremely high. Right? So all this is there in the textbook, but I just wanted to put that in perspective. So one thing that you need to remember when you're looking at the parachute as example, when you're studying air resistance, is that there are two instances wherein the R equals to mg condition is reached. One, when the parachute is opened and the surface area of the person increases drastically, causing the air resistance to also increase drastically, causing a reduction in speed, which is counterproductive because the air resistance now reduces. So this starts playing a major role again, and it starts pulling the object down. So as this pulls an object down, it accelerates again, so its velocity again increases. So this again increases, till again a time is reached when mg equals to r is reached again, but now at a much lesser velocity because surface area of the object is increased, and the constant velocity that is required at mg equal to r in the second time round is far less, and is much safer for the person to land on hard ground. So this constant velocity that you're looking at over here when r equals to mg is called the terminal velocity. All right. So mg equals to r means constant velocity, right? Newton's first law. I guess everyone got that. Okay, so with that, we come to the end of our discussion for this video. I'll see you later. That's all for today.